Thank you very much. So first of all, I would like to thank the organizer for the invitation and for the opportunity to participate. So this is part of my PhD topic under the supervision of Professor Yusuf Mameri. So previously, it was already discussed what is dengue, but please allow me to give a short introduction. Yeah. So dengue is a mosquito-borne viral infection found in tropical and subtropical regions around the world. In most cases, dengue is a self-limiting illness. When infected with one strain of virus, you will be immune all throughout your lifetime. But when infected with a new strain of virus, a more severe form of dengue will occur, which is known as the dengue hemorrhagic fever. So for decades, a vaccine was being made, but the first commercialized vaccine was known as the CYD-TDV, marketed as Dengue-Dengvaxia by Sanofi Pasteur. It was licensed in December 2015 and approved in 11 countries, including the Philippines. So I highlighted the Philippines because I am from the Philippines. That is one of the reasons why I am interested in this topic. Dengue-Dengvaxia is a live attenuated ceramic product made using the recombinant DNA technology by replacing the pre-membrane and envelope structure genes of yellow fever 17-day strain vaccine with those from the 4 dengue serotypes. So Sanofi Pasteur recommended that it should be given in 3 doses with 6 months apart for individuals of age 9 to 45 who already had previous infection of dengue. So with this in mind, we were able to develop a model using the Ross type model, where the orange one are for the human population, and this is for the mosquito population. So we call the SH as the primary susceptible humans, or those humans who have never been infected by dengue. And we denote the SH tilde as the secondary susceptible humans, or those humans who have previous infection, either by first, second, or third infection. So in this model, I want to point out that RH, or the recovered humans, are the humans who have already been recovered from all dengue types. So if you have a previous infection, if you have never been infected and then you infect at some point, you go to the infected human. Once you recover, you go to the secondary susceptible humans. But once you recover from all strain of virus, you go to the recovered human. Okay, so from this, we have this dynamics, which is just pretty basic. So since the human population, or the death of human is meager compared to the death of a mosquito, we neglect the death rate of human. So we have the ABH, IMSH over H as the probability of the primary susceptible humans to be infected by mosquito once it's bitten by an infected mosquito. And the ABH tilde as the probability of the secondary susceptible humans to be infected. So in this dynamics, we consider only the constant human population. And for the mosquito population, ABM, IH over H, SM as the probability of the susceptible mosquito to be infected once it bites an infected human. And in this dynamics, we consider an entomological growth model for the mosquito population, which is based on the paper of Billman, Cardona, Salgado, Dumont, and Vasilyeva. Okay, so with this dynamics, we were able to obtain a global Wilposeness result. And we also obtain 2 disease-free equilibrium, wherein we get an RO, which is equal to this one. And this RO is only biologically meaningful if our alpha M is greater than our mu M, which basically means that the average number of new infected humans is proportional to the transmission rate due by biting during the infection period and mosquitoes' life expectancy. So with this, we were able to prove that our disease-free This is free equilibrium A1 is globally asymptomatically stable if our alpha m is less than mu m. And if our alpha m is greater than mu m, given that our RO is greater than 1, we prove that A2 is globally asymptomatically stable. So with this dynamics, we plan to add the Dengue-Dengvaxia, which is, we did not take into consideration the age structure. So remember, Dengue-Dengvaxia was recommended to be given to individuals between age 9 to 45. We did not yet incorporated that. That would be in our future study. So we only focus on the recommendation that the Dengue-Dengvaxia should be given to individuals who have previous infection. Okay, so in our study, we apply two control strategy. First, we have the vaccination, and then the vector control, and we also try the combination of vaccination and vector control. So with our ODE, to apply for the vector control, we simply put the VMSM and VMIM, which is VM is just the rate of applying pesticides for the mosquito. And we put V1SH and V3SH, meaning the vaccination of primary susceptible and the vaccination for the secondary susceptible. So with these control strategies, we denote the total human immunity to be V1SH and V3SH, or the primary and the secondary. They are the immune human. And for the vector control, we have the VMSN. Okay. So in this system, we were able to get two equilibria, and we were able to show that they are globally asymptomatically stable if the condition for alpha m and mu m plus Vm is get. Okay, so from here we apply optimal control problem to determine which is the best control strategy to minimize the infected human. So we apply A1 as the effort in vaccinating the primary susceptible, A3 as the effort in vaccinating the secondary susceptible, and AM as the effort in applying pesticides to the population. Okay. So with this objective function, subject to our variable state, we were able to obtain a result that there exists an optimal control, we call it as W star, such that our J is just the minimum of our objective function. So from this lemma, since the optimal control exists, we use the Pontryagin maximum principle to obtain what is this optimal control value. So by applying this Hamiltonian, by applying the Pontryagin maximum principle to the given Hamiltonian, we were able to obtain a backward in time solution of our ODE, subject to the condition that our lambda sub t is equal to 0, so it's backward from the final time back to the 0. And we were able to get this as our optimal control variable. Okay? So from these previous theorems and lemma, we apply a numerical simulation wherein our datas are taken from Brazelton, which is from Indonesia, which is closely close to Philippines. Okay. And we have this algorithm. So given an initial condition, and we choose our W1, 2, and the WM between 0, 1. So first we get the forward in time from 0 to the final time t. Then we apply the Hamiltonian, final time t to 0. We call it as the backward system. And then we update our W sub m. So we have this as our numerical simulation. And from this numerical simulation, we were able to obtain this result. So as you can see, the Combination of vaccination and vector control is the best strategy if we're only to consider the number of infected humans. But remember again that there is a condition that we have, Dengue-Dengvaxia has a condition that it should be given to humans who have previous infection. So as you can see, it's not that good. Okay? So aside from this, we also have the primary, secondary, and all the other variable. Okay. So for the optimal control, this one is for the combination of vaccination and vector control. So if we consider only for the vaccination, it, of course, applying optimal control or application of the control is easier. I mean, apply shorter time compared to having the both control strategy. But I want to point out this one. If we only vaccinate the secondary susceptible humans, it takes a long time to vaccinate them. Okay? It takes a long time for them to vaccinate only the secondary humans. Okay. So with this in mind, we try to incorporate the life cycle of mosquitoes. Okay. Because previously, we only considered the adult mosquitoes. Now, in here, we try to consider the young mosquitoes. Wherein, we all know that adult mosquitoes lays egg. Egg goes mature into larvae, which is there are 4 stages. We call them as N-star. And then larvae to pupa, and then pupa to an adult egg. So with this in mind, we have this governing equation. Okay. Egg, alpha M is the birth rate of, or the susceptible mosquitoes and infected mosquitoes giving birth. Okay, so we call this as alpha M. And then the gamma of EL, gamma LP, and the gamma PSM is the probability of growing from egg to larvae, larvae to pupa, pupa to susceptible mosquitoes. So we assume that the infection in mosquitoes does not pass through the egg. So we only assume that all the emerging new adult is always susceptible. Okay. So in this equation, we apply 2 control strategy, which is copipad for the young mosquitoes and pesticides, just like the previous, for the adult mosquitoes. So what is copipad? Maybe you already know, but it looks like this. It's very small bacteria. And it is a natural enemy of the first and second N-star. So they are only concerned on the first and second N-star larvae. So if you apply copipad, its effect is only on the larvae, not the eggs, not the pupa. Okay? And then the pesticides. Okay. So applying for the copipad, based on the previous equation, since it only targeted the larvae, so we just subtracted it by W sub y, L. And for the pesticides, we have for the susceptible and for the infected. Okay, and from this one, we were able to get this result. So taking into consideration only the copipad and pesticides, it's best for the elimination of infected humans. But if you consider the pesticides and the vaccination only, it does not really eliminated the infected humans. Okay. And also for the infected mosquitoes. The best of the 2 strategies is still the copipad and the pesticides. And this is our control variable, optimal control, which is this one is for the copipad and the pesticides. So with this one, I have the conclusion. Optimal control showed that vaccinating only the secondary susceptibles offers few benefit compared to without control, and constant effort is necessary. Our result also shows that the combination of copyped and pesticides is a good strategy for eliminating infected humans and mosquito population, although the elimination of infected humans is small. And the combination of pesticides and vaccination seems less efficient than the combination of copyped and pesticides. And it takes shorter time to reduce the number of mosquito with a reduced duration of application of the control. So our in progress are optimal control with spatial distribution. That's all. Thank you.
Okay, thank you very much for this nice talk, Cheryl. So, any questions or comments in the room? Yeah, Vasil.
Thank you very much for the work on the perspectives. I have one question about the cost function, because I noticed that you said that, if I understand well, applying the vaccination is not that efficient in your results. But as I understand well, it is not meant to block the infection, but just to reduce the number of serious cases. People which are going to be infected twice and which might suffer from hemorrhagia. So my question is it part of your control strategy to reduce drastically this number, or is just that you count all infected equivalently in your cost, and then it would explain why it's not so efficient to apply this vaccine, because maybe my question is whether the cost function is really meant to measure how many people could avoid this secondary infection, which seems to be critical.
Yes, yes. As you have said, we just consider like all of them, not really take into consider for who has been infected twice, thrice, or fourth. Just all of them. So yeah, we will. That's also one of the reason why we say that the secondary susceptible as vaccinating secondary susceptible humans is not that effective. It's because of our A3.
But that's mainly the reason why you don't vaccinate the primary susceptible. It's not to put them in the risk of having a hemorrhagic dengue, right? So, and once you have it once, then it doesn't change the risk when you have it between having it once or twice.
Actually, it changed the risk.
It continues to change with
Yes.
the number of infections.
Yes.
But you don't take that into
We
account.
did not take that into consideration.
Okay. And also, I had read that the vaccine itself is not equally efficient against the 4 serotypes, which could also determine your vaccination strategies depending on serotypes, right? And the thing is that you would get a system with too many equations, but at least numerics, you could be able to do it, no?
Yes, actually, that's the reason why we did not divide properly the susceptible humans. Because if we're going to properly divide the susceptible humans, there should be S1, S2, S3, S4. I mean, those S are for who has been susceptible for another type. Okay, that's the reason why we did not subdivide it into that form, because we do not know how to get the parameters. We have no data yet for that one.
Okay.
So we just generalize them.
Yeah, it's already a nice approach. And the thing of using these natural enemies for your larvae instead of larvicides, that would be interesting from what point of view? It's very easy to apply this copypod strategy?
Yes, because copypod does not really affect other organisms. Okay. They are only interested on the end star, the larvae, the first and the second end star of the larvae. And once, for example, a fish will eat the copypod, it does not affect the fish.
Okay.
So that's why we are only interested on the copypad.
Copypad. Okay. And in practice, they use them in the Philippines or in Indonesia?
Not yet, but we
okay.
are, after this one, we are trying to submit a proposal to give it a try to the Philippines because it's more, less costly compared to Wolbachia.
Yeah, sure. Sure. Okay. Any other questions or comments? Okay. Also, I think we can thank Cheryl and have a small break.